Znači, upao je u ovaj strana na listu, što je super, i nije ti došlo dobiti špirat, to je najvažnije ti.
Ja sam mi prvo odgovorio kad sam napravio.
Sam, poslali su mi samo dijeliće, kumbiće, sve sam tamo.
Kad je ENCORE? ENCORE nije ovdje, bit će u Ateni ovdje. Znači,
Haha, ali imate program će.
Da, program će, bit će 22. Ovdje treba biti u Hrvatskoj, ali očito je ove godine Kimon popušio brdo pare, onda su ga Grci stisnuli, nisu mu dali da ode iz Atene, jer smo mi već i dobili draft ugovora s hotelom i sve. I pošaljem ugovor Kimonu, ne javlja se, pita Maju šta je s Kimonom, on veli, pa čula sam se s njim neki dan, izgleda da ovoga neće moći biti ENCORE 21. u Hrvatskoj, pa ono, boji se i srami se, javiti se, kao, kužiš onak, ne? I onda fakat on nikad nije rekao da neće biti, nego samo odjednom je poslao e-mail svim članovima ovoga, azijatskog komitija, kao, vidimo se sljedeće godine u Ateni, ne? Aj si baš peder je, šta sad ono, i onda ja se isto pravim onda kao, ne pojma te ono, hajde ono, s tvojeg e-maila zaključujem da neće biti u hrvatskoj konferenciji, ali onda on kaže, da neće ovoga, bit će Ateni, bit će 22. Dobro, kaj će sad s hotelom? Nisam dogovorio se ti petak, preksutra, ćemo imati Skype sa hotelom, da on nima, ja nisam te sve rekao, dobro, ti ćeš kao organizar objasniti njima zašto vi u Hrvatskoj. Sad me broj zanima.
A koliko je
Valmar.
Ne koristi.
Da.
Pa ne, pitaš kako može izgledati.
Ma nema, naravno da će to i hotel će to napraviti. Ono, tako kurinski ponašanje, kako je možeš od Grka očekivati, ne? So again? Building information model. This is a set of software for models of it's like a camp, but they don't get the
Real estate stuff. It's talking to the innovative buildings.
Real estate, yeah, buildings, yeah.
Ah, okay, stock, I thought it was like livestock or something. Real estate stock. It was like what?
Buildings.
So this is like you would use 30 pieces of cloth to do outside.
Everything, yeah. Because they're running around the buildings, so it's pretty model.
Professor Vukic joined us.
Very nice. Pa ne, zato mi je ovo ostalo od review meetinga, pa mi se nije dalo mijenjati. Iako je Marko pripremio super template. Ali dobro, ne, Marko ga nije koristio. Marko je koristio template. Matko je barem nešto naravno nešto ima.
Činjenica je da nisi koristio.
Da, činjenica da je ovo čista lana stranica. Samo ja ne vidim bolje.
Da. Kao što je rekao Frano, to je lagani prijelaz prema plavome. Od narančastog. Ja, sure, I'm ready.
Good morning. Good morning, welcome to the third BTS 2020. I want to read the whole geography. I think everyone knows Professor Bogdan. He's a new professor at Kvasić, FER, and he has been a principal investigator and researcher on 28 national and international scientific projects. Among them, ENCORE, and Maritime. Today we'll be hearing about ENCORE, in particular about data acquisition service for this project and the UAVs that will be used to capture information for this service.
Thank you, Fausto. Good morning, everybody. As Fausto said, today's sessions will be mostly oriented towards the aerial robotics. Later on, after 11 o'clock, we have 3 talks that are related to aerial. And we will start the day with this one, which is about ENCORE project that currently we are running. We are at the 2nd year of the project. We have 16 months in front of us, and today I will present you what we achieved so far. First, before I start, as you all know, there will be nothing of what I will show you today without those people. So credit goes to postdocs and PhD students that are involved in research. If I would like to present you what is ENCORE about with a single image, then this will be the image, because there are 2 things I think that is particularly proper image to demonstrate ENCORE. First one, because it's very fancy and very nice, and the second one, because it's really indeed describes what is ENCORE about. So there are 2 words in the title of the project that are very long, and those 2 words are renovation. This is the first thing, and the second one is energy. So those 2 words are the most important words in the title. Why? Because as you know, in Europe, there are huge number, hundreds and thousands of very old buildings that actually are not energy efficient. So what we would like to achieve in this project is actually to see how we can make a process of renovation of those buildings to be cost effective and also to be such that we can save energy, to make it energy efficient. Most of those buildings that are very, very old, actually, there are no blueprints how they were built, or if those blueprints exist, they are not digitized, they're in a paper form. So for architects, in order to make those renovations, it's quite difficult to prepare a process of renovation for construction workers. So what we would like to do, we would like to gather data. That's why I will talk today about data acquisition service for ENCORE architecture. We would like to collect data of those buildings by using aerial vehicles that are equipped with lasers, cameras. So we would like to fly around the buildings and build a model that will look like this left side of the image. We will have a photogrammetry, we will have a point cloud. But this model, which is very fancy, very nice, and most of you already seen such models, there is huge hype about this kind of models, but those models are useless from the architecture point of view, because architects actually cannot use such models to prepare CAD drawings to actually explain which type of windows, which type of doors, which type of roof beams will be used by construction workers in order to renovate the building. That's why we, from this model, which is on the left side of the image, have to go somehow to the model that is on the right side of the image that actually demonstrates the stuff that is used, that are used by architects. So the process from the left to the right is actually ENCORE. Once we prepare, architects prepare the process how a building should be renovated, then other parts of ENCORE architecture are there in order to follow how construction is done, if it's everything on time, how much it costs, etc. So this is also part of ENCORE platform. Now, to wrap up, what are main objectives? As I said, we would like to provide effective and affordable BIM. BIM is abbreviation for Building Information Model. This is nothing else but a CAD for architects. There are many, many BIM tools, and one of the few of those BIM tools will be incorporated in ENCORE architecture. Then, we would like also to provide the mechanisms and tools for dwellers, for people, for residents that live in those buildings to be able to validate how project is developing. For example, if architects says that window type A should be put on the building in order to make building energy efficient, then owners should be able to validate if really this window A is on the building. Okay, then once we have this preparation of the process, what we would like to do, we would like to use ENCORE to automatically generate plan how this renovation should be done, which windows should be installed first, and doors, and beams, etc. And finally, as I said, this energy is the second word that is most important in the project. We would like to monitor how energy is consumed by the building and if we really achieve energy efficiency by renovation. So, what is shown here is the process that I just described. What you see on these photos is actually pilot case. This is the site in Kvasić, a city in Spain. There are two buildings there. One building is a building that is used as a, how to say, to collect the data, to be a model of a standard home. And then there is a second building where we put different type of windows, different types of air conditioning system in order to see how we can save some energies. And as I said, we are going to use UAVs to make the point cloud and photos, and then from this image in the middle, architects will build the model that is on the right side. This is described also here, so those steps that we have to do in order to get this model for renovation. This is the architecture that you see here. So we have several layers. First layer is actually data source. As I said, we have to get somehow all these data that are related to the buildings, because as I said, in many situations we do not have the drawings, we do not have additional information. So those data sources are actually BIM objects, which are objects that actually the model is built of. Then this is the part where we participate. So the programming leader in order to enable sport cloud and photos. Also, we are planning to use information from the sensors. If there are some sensors in the building that measure particular properties of the building, we would like to get those as well. Then we will use weather forecast systems in order to be able to see what is the environment in which building resides, and finally data from these systems in order, because it's not the same if building is in Spain or in Norway, then renovation is completely different. Once we have the data, what we will do, we will put this data into the core engine, we will process those data, and finally we will have those applications that will be used by architects or by people who plan renovation in order to achieve the goal to save energy and to renovate the building. So this is the place where this data acquisition service, actually this is our part of the project that is done at the Faculty of Electrical Engineering and Computing at University of Zagreb. There is special task in the project that is development of this data acquisition service. As I said, we are currently in the month 21, so we have 15 months to complete things that are written in those tasks, these tasks. Okay, what is data acquisition service workflow? How we imagine to do this? First, we will have a ground station, and on this ground station, there will be a platform application that will get the data from Google Maps and also from Cadastre. Once we have this data, then operator that would like to make this point cloud and photogrammetry of the building will put the waypoints in order to set the layout of the building that we would like to fly around and take the data. So this is the second step. Once those waypoints are entered into the system, then our application should plan trajectory for the aerial vehicles. The main idea is to do the job with 3 aerial vehicles autonomously. So we will need to plan trajectories for all 3 vehicles in order to fly around those waypoints that are describing layout of the building. Finally, once we have trajectories, we will execute the mission. And after mission execution, we will get the data, as I said, point cloud and images. And those images and those data sets will be processed by our colleagues, our partners in the project, CNR and ETH Zurich. So this is the workflow of a data acquisition service. Components of the system that we are building, we have 3 main components. First is the ground station, which is actually a computer that serves to as communication point between the operator and the UAV system. Then we have 3 UAVs, and finally we have RC control station in order to take manual control of the vehicles. And as you can see, each of these components is comprised of a hardware and the software modules. Now, I will briefly show and present each of those components. First, unmanned aerial vehicle. As I said, we bought 3 of those vehicles that you can see here. These are the hardware structure of the vehicles. As I said, we have a Velodyne light lidar. This is the, I would say, main sensor on the vehicle. We have a Z mini stereo camera, SmartTech camera, Intel NUC computer, and also neural stick for data processing. Payload of this vehicle is somewhere between 1.5 to 2 kilos. Software that is running on these aerial vehicles, we have piece of autopilot. So there is a trajectory tracking controller, all following controller, impedance controller, and attitude controller. What we achieved so far, we have a trajectory tracking controller, an attitude controller, and what we are working on and what is in front of us in the next year and a half, we have to make all following controller impedance controller, because we would like also to collect the data about the properties of the wall of the building, which means then we would like to find a point on the building when we can get in touch with the building, and we will use electromagnetic and ultrasound sensors and scan parts of the wall in order for architects to know about the material that the wall is built of, and also to have information about the thickness of the wall. Here's the structure. I'm not going into details of structure of control. We are all here from control community, so we know how this works. And this is how we imagine this wall following controller should work. So this is the structure of the controller that should be built. There are some results that are already published, but we still have to make experiments. Ground station, standard laptop, only managed touch screen capability, and since we are planning to go outside in the field, everything will be placed in this case. Ground station has a Linux system, and the main purpose of a ground station, as I said, is to serve as a human-machine interface and also as a mission planner. So trajectories are planned on the ground station, and then they are uploaded to the vehicles. So as I showed on previous slide, once we have a building layout, so this is the building layout, then we plan those trajectory points by using Huygens principle in order to keep the vehicle all the time at the same distance from the building, and orientation should be perpendicular to the wall. This is the GUI, how it looks like. We have 3 vehicles. You can select which vehicle you would like to track. Telemetry, standard stuff that actually every operating station should have. Now, the last part of the ground station is, as I said, the part of the interface that demonstrates the position of the vehicle in a GMAP, and also that takes data, gives data from cadastre. Once we extract GPS coordinates of respective buildings, so this building that you see right here is a building in our campus in Zagreb at Borongaj. The red one is the vehicle, and when we have those positioned, then we just get the data from cadastre. For example, in Spain, those GML files are free of charge, but here in Croatia you have to pay, I don't know by heart, but some amount of euros in order to get this data for this particular building. Once we have a building, you will see the process when later on I show the video clip, but those orange points are actually those points that operator sets in order to present to the system the layout of the building. Okay, so first, what we did so far, we did experiments in the simulation, and what you will see here on this video clip actually is simulation in gazebo. On the left side of the video clip, you can see images from 3 cameras. These are 3 cameras of the 3 vehicles that are near to the building, and trajectories are planned, and then first vehicle takes off and starts to move towards the building in order to execute the trajectory that is pre-planned. So we have 3 trajectories that are same but at a different altitudes in order to scan the whole building with just one fly of those 3 vehicles. So you can see those images that are acquired by the vehicles while they fly around the building. So everything has been tested in simulation with the graphical user interface that was also connected to Brazil. And those data, as the vehicle flies, are collected, and later on, from those images, we do photogrammetry. Also, laser scanner is mounted on the vehicle, and there are laser scans of every part of the building. So once we confirm that things are working in simulation, the next step we have manual testing. Here you can see students, PG students in the campus Borongaj. This is old military facility. This is old military building that are not inhabited, so it's perfect for experiments where something could go wrong. You're not going to hurt people except PG students, but they're not considered as a people usually. Okay, so here you see part for the calibration of the system, and then once we flew around those buildings in manual model operation, these are final results. As I said, our partners for this actually are partners that should be called as models of buildings that we provide on clouds and photographs. But what we wanted to do, we wanted just to see how our system works. So you see those buildings that we scan. Over here you see trajectory manually building in order to get all this data. And we flew with a single vehicle. Again, because of the security, we just wanted the safety, wanted to see how it's worked with a single vehicle. Finally, last video clip that I would like to show you is actually mission execution with one UAV in autonomous mode of operation. So what you can see is a GUI, a stripe. We have telemetry data over here. This is the part for the trajectory planning, and you see here this window that shows data that are required from GMAPs cluster. And you can see this building in our campus over here, it's a vehicle, and now operators should set points that will show the layout of the story. Layout of building. So now we uploaded data. Now those orange dots that you can see up here, actually those are waypoints that operator enters manually as part of the building. And then based on these points, we find out layout of the building. So this is blue. Blue is the layout of the building, and then trajectory is planned for the vehicles. And finally, we have results. So blue is UAV trajectory, and red are those dots. And once we have the planned trajectory, the UAV mission is executed, starts, and it takes images and LiDAR scans from the building. As I said, this is a mission with a single vehicle. We have to make experiments next spring with all three vehicles and also all buildings. In this particular experiment, we didn't execute full trajectory, just half of it. Now you'll see the data that we collect during the flight. So those are images that are taken by the vehicle. And also, we're taking those LiDAR scans. Everything is on the vehicle for processing. And the final part of the video is actually data acquired by LiDAR, which we are using the SLAM because we use GNSS for navigation, but also we are using information from the LiDAR node to navigate the vehicle. Okay, so what is the future work? What we have to do by the end of the project? As I said, we have to prepare and execute experiments with the UAVs, and everything should be done in autonomous mode of operation. And also, we should prepare user interface to be used by non-professional pilots. Then we would like to improve the quality of point clouds and the photos, because in order for our colleagues to be able to go from the 3D model to the building information model, which showed on the first slide, we have to very precise in clouds. We have to acquire more data set. And finally, what we have to do is to prepare this whole quality control in order to be able to take ultrasound and information from the walls. Okay, so this is all from me. Thank you very much for your attention.
Thank you. Questions?
You showed me in one of your images the checkerboard for calibration of the camera, but are you calibrating everything with respect to behind you? And how are you doing calibration of LiDAR camera for extrinsic calibration? So is your plan to do some fusion of RGB depth and therefore needing a calibration between LiDAR and camera?
Okay, so maybe Anton could reply to this question.
Okay, so basically, we do everything in the UAV frame, in the UAV frame. There are methods to calibrate camera to IMU. We also calibrate the LiDAR to IMU, and then you have
solved it basically.
When doing trajectory planning, certain points around the building, and the question is, so when the vehicle performs the trajectory, does it follow those points using GPS, like actual navigation, or is it relative to the building? And if it's not relative to the building, why not?
It is relative. So, as Anton said, it's sensor fusion. So we use both. So we use GPS navigation. There is the common filter on the vehicle, estimates position based on the GPS, and also we are using cartographer. So we are using also data from the laser cameras. So there is sensor fusion on the vehicle. And also for the wall following, in that case, we use just LiDAR. For example, there is a paper published where we track the surface of the blade of the wind turbine, and in that case, we rely only on the LiDAR, and we measure distance based just on the LiDAR. But in this particular case, I think we were using GPS and we followed this particular build. Yeah, and this is still a question, especially if you lost communication. Especially if you lost communication, but most of the vehicles they have return to home position. So, and they use the strike line to return to home position. So, but that's why we just need this half of building for security reasons around. This is the issue that we see.
Another big question is mission continuous monitoring. So after the building is renewed.
Exactly.
In the writing proposal, you have to have special care of ground system. Because many people are some betting in the robotics.
Yeah, there's a lot of ethical issues, but usually there are no dwellers inside or residents inside the building with their renovation. So in this sense, you are allowed to take images of the building. But later on, what other guys are doing, typically our colleagues, they are planning to install sensors inside the building to track this comfort, track energy efficiency. We are not planning to use any cameras inside the building, just sensors that measure usual power system. That currently there are no such systems in these buildings, but managed to put also this inside.
Other questions?
Yeah, this one it is, but they didn't notice the before. I don't know if they complain after. Nobody was there. Okay. It was a Sunday probably.
There's a car.
There's a car.
Yeah. Okay, thank you very much.
Thank you very much. Next talk is by Kvasić, our technical problem also. And he's a researcher and PhD student at the UNIZG-FER, and he's also a member of LABUS, Laboratory for Robotics Technologies. And he's currently involved in the Adriatic project, advancing robot direction capabilities. And the talk will be about sonar-based robot direction.
Great. Good morning, everyone. Thank you, Fausto, for the introduction. And as you said, I'm going to be talking about object detection. Object detection is a key element of computer vision tasks, robotics, especially considering autonomous robots, whether on land, in the air, or on the water. Not only only that, it comes in handy in lots of other operations like phase detection, phase recognition, medical diagnostics, so on. So the motivation for this research comes from the CADI project that Jula talked about yesterday, which envisions robot diver interaction in the form of a robotic diving body. And whether through one of its functionalities, where the robot observes the diver, where it helps the diver carry out a task underwater, or it guides it towards a point of interest. The key in making all three of these scenarios possible is for the robot to have some kind of perception of the diver. So, in addition to that, through the Adriatic project, which was one of the main goals, is researching novel diver-robot interaction capabilities, besides all the modalities that Jula talked about yesterday, such as the gesture recognizing lab, or the haptic feedback, or using flashing lights as a form of a diving body line, red or green LEDs. The idea is to use the motion of the vehicle as a form of interaction, as a form of communication with the human diver. So when I'm going to be talking about object detection, I'm mainly going to focus on detecting human divers. So the idea, the objective is to achieve a reliable and robust way of detecting divers inside a sonar image. So why would we use sonar instead of a camera? Well, the problem is that cameras, by increasing the water count between the robot and the diver, it quickly adds up, and the visibility, the optical visibility, drastically decreases. And sonar, being an acoustical device, does not depend on the optical visibility and is able to detect the target, to detect an object at much higher range. So this is how some of these sonar images look like compared to their camera counterparts. And in case you've been wondering why do we get this fan shape, or why do we get like sort of a top-down view diver while we're pointing straight at him, that has something to do with how the sonar image is constructed. So the multi-beam sonar has a number of beams that shoot acoustical signals, and use beamforming to measure the intensity and stack it in an array over time to create this kind of image. Because these beams are under different angles, get distortions in the image. So in order to get rid of this distortion, you convert it from Cartesian to polar coordinate system and get this kind of image. In case you haven't been wondering that, let's do that. So far in my research, I have been using two types of sonar. First one is the RX Explorer 3000, which is a dual frequency 1.8 and 3 megahertz sonar, which gives really nice high detail, high resolution sonar images. The downside is that it has relatively low range and relatively low 30 degrees horizontal, 50 degrees vertical field of view. So it's easy to lose sight of an object you're tracking. In addition to that, it's sort of a big unit at 6 or 7 kilos. And the second one I've been using is Tritech Gemini 720, which has 512 beams at a slightly lower frequency. So you get a bit less detail, a bit less of angular or range resolution, but you get a much greater range and you get 150 degrees field of view, which is nice. And at 1.5 kilos, it's easy to mount it on any robot. So the robot we'll be using is a D2 vehicle that you had the chance to hear a lot about yesterday. So I'm not gonna go into that. So the first idea was to create a data set and to use existing emotional new networks and just see how they perform in detecting something in the sonar image. So we did that. We created a data set consisting of 2,000 labeled images and 200 relation images, and just have had different CNN architectures. Go to that same data set and just see how they will perform, and this is the results we got. Of course, one of the main considerations here was speed of execution as well, considering it has to run a mobile robot, where some of the architectures with a lower number of layers will be much faster, with not that of a significant drop in performance. So this is some of the results we got, and see that they were pretty promising. And the reason the mean average precision, the usual metrics were used to compare performance, do not give extremely high results like the 90s region, and that is partly because it's a non-convex object, and sometimes even for a human, it's difficult to tell if the diver is set in horizontal or vertical. Can we see the fins, or is it just acoustic shadow? So even the networks have sometimes trouble determining the shape of the bounding box itself. From those results, we decided to collect a bunch of more recordings to expand the database. Recorded divers in different environments, in different backgrounds, doing different motion patterns, and also using different sonar, and where the ARIS recordings were really detailed, really high resolution. The Tritech ones, when you look at the footage, it's somehow easy for the diver to blend in with the background. And if you look at a single image on the Tritech sonar, it doesn't look that detailed, especially this light. It doesn't look like you could recognize the diver in it. So it needs some pre-processing in order to become useful for detection. And if you plot the histogram or the density function, you can immediately see that there's something wrong. So we applied some basic histogram polarization techniques in order to get this image. So this spike, the 0, just mask that I applied on the edges of the fan shape. And this is the before and after result. You can still see there's a lot of noise going on, and we tried different denoising techniques, but they all just seem to kind of smudge parts of the image and do not contribute with any new information to the image itself. So the idea of this part is to collect a database and in order to create database that will be publicly available, because unlike for some objects that you had the chance to hear about this week, like peppers, tomatoes, there are large publicly available data sets, label data sets with tens of thousands of those images, which is just not the case when it comes to sonar. So the idea of this is to create this database, to publish it publicly, so people could use it and it could serve as sort of a benchmark for people all over the world to use it. So since then, we upgraded the sonar to a dual frequency model, which at 1.2 megahertz should give high resolution and higher level of detail and solve some of those problems, while still maintaining 120 degrees field of view, which is nice. We haven't really been able to use that one on divers yet. Somehow all our travel and field experiments we got planned for this year got either postponed or canceled. I don't know why. It all started when Croatia took over the presidency of the European Council. I don't know if that's a coincidence. I'm not saying it's not. So besides that, we had a dedicated CPU for image processing. It's an NVIDIA Jetson Xavier, which is a really powerful CPU and GPU unit, relatively small 10 by 10 centimeter footprint. And hopefully we're going to get the chance to test it and to do some live detection this BTS. So with that, I would conclude my presentation. Thank you for the attention, and I'll be happy to take any questions.
Thank you. Since you actually, you mentioned fictional object, actually you talked about diver. So, is it diver or is it logic? Because if you know that you're diver, maybe you just move the ground, such else, to see if you get the help, or you're really trying to find any kind of object on the
So the techniques I'm using are ideas that will be applicable to any kind of object. Because the two projects we are working on, the main goal was to detect divers, and the idea is to detect it from a robot that is moving. So you cannot get filter out, not easy at least filter out the background, and that is why I on this way subtracting the background, focusing just on the diver shape. And it's anyway it's a complex shape. But depending on the diver position, it can take a lot of different shapes.
Yeah, you have a very, very difficult task. Related question. Are you considering tracking the shadow of the diver? And then also, are you, Jula mentioned yesterday, like another sensor that can be potentially used for fusion, but just passive reflector or something putting on a diver, having that set up might be worth trying, because you're, making these data sets available, and that's really great. I think that's a very important part of your work. but then maybe he has some recordings with the reflector of a sort, maybe something that could be made for that specific frequency of the unit that you have.
Great question. For the first part, panel is not always available either depends of their direct position, whether also bottom, etc. Shadow happens only when you need the bottom. So I have been thinking of using some other features like air bubbles or like that to detect the diver, but the shape of the diver body more promising to me. And for the second part, that would kind of limit to a single application with a specific reflector on the diver. And the idea here is to be more general, to be able to detect maybe multiple divers, maybe be applicable in some kind of surveillance application, etc. So I didn't really focus in that direction.
More questions? I have one thing to follow the same. In the others one, you can see the object. In the contact one, actually, I can see that the shadow of the object. So I think it's worth to try at least for that sonar, try to analyze the shadow. Because shadow is black, so the other one you have white and you have very noisy area with the visualization. While the shadow is black and you expect it to be behind the object. Things of course the distance and the inclination angle going to be, and try to find in an area around the object behind.
That's a good suggestion, but as I said, really for that kind of shadow to happen, it really has to be positioned at a certain angle, and it has to be close to the bird plane.
Any other questions? Thank you. We now have Maritime Kapetanović. Maritime is also a business student with different projects. He is involved in different projects, but currently is more in the project sector. And similar to Igor, we'll be speaking about online seabed coverage planning for autonomous system vehicle based on some.
Thank you for the introduction, Pastor. Today I'll talk a bit about lightweight delivery loopers, the current planners, and the processes that we set and so on. Actually, our knowledge about our planet generally is evolving through time, constantly. Now, oftentimes we know much more about other planets and their moons than about our own oceans and seas. This knowledge is crucial with the missions for mapping, documentation, and monitoring of our oceans and seas is very important. Robotics can actually help quite a lot in this task compared to the classical methods using ships, research experts, and very expensive equipment on the ship engine. An example of the use of marine robotics is actually the use of autonomous underwater vehicles, or AVs for short. Their pros actually compared to the classical methods of monitoring are their range. So they use sensors, for example, seismic sonars, which have a much bigger range than human divers. Inspection missions, they're completely autonomous, so there's no need for any human interaction, for manipulation, etc. And at least in the long run, they seem to be cheaper than renting a boat with the experts, the divers on each inspection mission. On the flip side, the system is quite complex. It needs to develop the autonomous seafloor exploration for coverage processing of sites and sonar data, and to define a generic way of some interesting objects which could be found at the seabed in order to inspect them in more detail. So a bit about early Lucas and its hardware. Was actually acquired by our laboratory a few years ago from the Ocean company from Portugal, and there's this kind of DLSS approach to Lucas has actually three parts. The front part, which is wet with CTP sensors and other equipment for measuring like environmental parameters of the seas. The main hull where the whole electronics and sites and sonar, the front side and the basic computer are located, and the tail section with the DC motor skins on camera mode. So for the software, LSTS has developed their own toolchain for controlling and planning missions. So they have this whole trinity of models. So Netus doing IMC, where Netus is used as a mission planning, execution, and review analysis tool. UNIZG the core piece of software which encompasses controllers, navigational filters, etc. And the IMC module which actually interconnects all of these modules through IMC message. Something similar to ROS, which is still going to be the basic Linux-based filter, and some of the libraries which we use to control, for example, the LAV by the method of monolithic controller, output, and OpenCV for the dimension size and sonar infantry processing. So how does the seabed look when we record our sites and sonar? So as you can see, here is the so-called vertical view of sites and sonar. The acoustic return things stacked together in one line, which the vehicle has passed. It's mostly sand or mud sediment, with quite a few interesting protruding objects, which could be of some interest for the research. So the vehicle goes along the one line and then goes back to see the same objects but from another side. So one of the major pros of sites and sonar use is that it shows, as opposed to the multiple sonar, the morphology of the seabed. And the brighter the return thing, the harder the material, for example. So it would be very useful for classification of the seabed in general. Okay, so there are two methods which the inspection, like the manual human plans, I should say, inspections are planned. One says, okay, let's do this mission as fast as possible, and we don't overlap any of the sonar slots. Just like a general overview, coverage by planning mission, to get the general idea how does this area work. In this scenario, the mission lasts much shorter, but the objects in their morphology is much less detailed because we sonify them just from one side. The other method is the opposite, and we call it classical coverage by planning algorithm, or CLCP for short, which says just the opposite. Okay, I want to overlap each sonar spot, and then every time I see an interesting object, I'll go back and we sonify it from another side to get more morphological detail about that. So going back to the motivation of my research, actually, to develop an online coverage path planning algorithm, which is based on the set and sonar data. And the idea is to start the mission, so to say, not adaptively, with wide long over slots, and then to replan the coverage path depending on the fact whether interesting objects were detected or not. And when they are, we replan. But for the rest of the mission, we optimistically assume that seabed is generally barren and that not much interesting objects will be found in the future. So going back to coverage path planners path planning algorithm is actually based on the path planning algorithm, which was the result of my master's thesis. And it results, so from some cost map, it produces this cost to go map. It's called like a 2.5D manifold, which brings this vehicle from any starting point to the set goal point on a known, a priori known cost. So the idea was to actually merge this path planning algorithm and then to use it in a coverage path planning framework and to say, okay, let's start the mission adaptively, and then when we do find an interesting object, let's diverge from the long molar line and actually plan this path based on the cost map, which is actually the substance on our data from this long molar line here. And then again, let's continue being adaptive until we find another object, make a loop back, same from another angle, and so on and so on. So this is actually an example of the performance of this algorithm where each of these already sent satisfying image is computed as a cost map, and then the cost goal map is computed for mission 2. So the next step was actually how to evaluate the performance of such algorithms. Actually, the first and the most intuitive is to say, okay, how shorter is our coverage mission compared to the classical CLCPP algorithm as we called it. So for each of the developed algorithms, we use the same performance measurement methodology, and for each of the algorithms, we ran almost 15,000 simulations with mission parameters variations to see on average in many situations how does this algorithm how does it behave. So here to the right, we have like a plain mission parameters, which I will not go into detail right now. But yeah, so we made actually divided this plane on pairs of parameters where our algorithms are better or worse performing than being non-adaptive, because yes, it can happen that being adaptive can yield worse results than being just non-adaptive. So because we are considering for the real cases only here, so this area of small values of mission parameters, we say, okay, this algorithm for our use case is going to be better, but can we improve it even further? So can we constrain the vehicle just to move along the long molar lines and to combine the classical two approaches of the operators into something which would be like a heuristic coverage path planning algorithm. And that's actually the basic coordinate coverage path planning algorithm. But to say, okay, like these are a few examples of back moving, not moving only along the long molar. So we see here great improvement actually of the performance of the area of mission parameters for which our new BTS algorithm is quite better than the subversion of CP. So we said, okay, we can be in some cases worse than being non-adaptive. So can we detect so this edge here between being in the green and then not wanting to pass deep into the red area, and to detect when we're on the edge, just to stop being adaptive and then to limit the lower performance down. So we say, okay, we developed the so-called extended coordinate coverage algorithm, which says I'm going to behave the same as BACTP algorithm, but then when I do reach this edge here for the given mission parameters, which is based actually on a huge number of simulations, as I said, I'll just be unadaptive to the end of the mission, just to cut off this lower performance bound. Okay, so we managed to increase the lower performance bound to make it tighter from first -20 for the BACTP algorithm to just about -7.5. Okay, so the last algorithm is actually to say the idea was to say let's not move just along the whole global line, just logically where we find something interesting, and then from that standpoint, the so-called optimizer coordinate coverage algorithm with a few examples of algorithms available here. Some loopbacks, so just where the object is located. And then we wanted to say, okay, just in the first 10% of each low moral line, then this algorithm yields even better results, or larger area of mission parameters for which it gets better results. So as for the mission planning execution time, it was interesting actually to see that, as expected, all the heuristic algorithms were 5 to 6 times faster than the dynamic programming one. So we actually stayed with the optimized accordingly coverage algorithm because it's the simplest and makes actually the most sense. Okay, so moving on to the processes of the sites and sonar imagery. We wanted to, so actually processing of the sites and sonar isn't the direct contribution of my PhD. So we wanted to make something generic to say, let's detect something which stands out from the background. Okay, so we're not doing any classification, just mere detection. Okay, so we wanted to model the human attention in natural images and the methods we use therein, which are called anomaly detection or saliency detection methods, and to see how well they transit to something like this, which is like a side-scan imagery of a bicycle, which was sonified from the side. So actually we see the morphology of the bicycle from the sonic shadow. So first up, we made a very simplistic simulated data set of the side-scan sonar, just to see to benchmark the performance of all 5 methods. This highly controlled environment data set, and so we had like 1,500 of these simulated images, and we compared all the 5 methods through precision recall analysis, and also the disaggregated harmonic mean, which aggregates, as I said, precision recall into just one scalar number, which says how well is this detection method performing. So as a result, the anomaly detection method got the best results, which we actually tweaked for even faster performance, and it had about 93% of this F harmonic measure. As for the execution time, since it's actually used for online processing, this method was the second best, so we actually chose it further to use it as our main method. As for the real science and sonar data set, we collected a huge amount of many, for example, underwater archaeological sites all over the Mediterranean, going from Croatia, Italy, Greece, and Spain, on many trials and projects actually, because everywhere we went with Lucas, we would turn on the side scan just to get as much data as possible. So we used this data set just to validate actually the method which performed the best on in the control method, and because it's a bit hard since it's not classification to say what's interesting. It's quite subjective, and if you have a flatter environment, then when everything is interesting, then it seems that nothing is interesting. So for these examples, we had like 350 real size and sonar images extracted from our logs, and the performance of the anomaly detection method seemed to be quite good, enriching the human performance. So moving on to running this method online on Lucas, actually on its Kvasić computer. Last year we had tests here at BTS, which yielded actually the performance quite good, even using Kvasić computer, which was, although it was 50 to 60 times slower than my laptop, for example, it was just fast enough for Lucas to process the data, just turning around from one low moral lane to the next. And so to conclude, I presented a few coverage pipelining algorithms, which are used for online actually seabed mapping missions by the use of sites and sonar. We've seen some significant reduction in mission time for the coverage path for these algorithms compared to the classical overlap course of all sonar spots methods, and also here 5 actually methods for processing sites and sonar imagery were tested and compared. The best one was then validated on a real sites and sonar images data set with quite satisfying performance. Thank you for your attention. For now, not, because the idea is actually to say if you collaborate with maritime archaeologists, okay, and they have like we had actually requests for some area to cover, and they say, okay, we suspect that there might be something. So the idea is to actually just for Lucas detect the area, and then to say, okay, if you find something, let us know in a way, and sonify from another side, so that the actual maritime archaeologists, when they say, when they see sites in some imagery, that they have more details about the morphology of the objects. So, yeah, sure. I mean, or we can make like a general survey, as you said, of the area, and then say, okay, this might be interesting, so let's inspect these objects of interest at a lower altitude, perhaps, to get like even more detailed, and also visual inspections, since Lucas has a camera, or to lower perhaps an ROV for visual inspection as well. Any questions? We privilege captain to extension, which is based on the length of like when you're comparing the issues captain knowledge, you compare only based on the length or condition. Yeah, basically it's certain coverage part. So in essence, how long does the mission take? Sure, maybe like even if it's a cost of one missions, you actually get better use of the object in some of the objects, especially the after one. Yeah, because you go fully around the object. Maybe it's a bit longer mission, but you actually get yeah, the trade-off between speed and quality. Yeah, exactly. Yeah, maybe you can see that should work. Yes, yeah, it could be longer mission, but not the other collaboration. I think so. Or it's because the professor will certainly. Everything is connected.
Maybe now to explain if you are doing and why we insist on having straight lines on our path, why we are focusing on
yeah, it's interesting because when we use sites and sonar, it's the most appropriate, easiest to exact all these things. And as clear as sites and sonar image as possible. And also, when you, for example, overlap two sonar slots in post processing, the most reasonable pattern is to use the one mode. Penić is also a system and new polymer systems. So position analysis of seabed. This presentation will be reducing the power local protection, but is a local structure theory project. And it's also the kind of the doctoral research project. Okay, hello everyone. We are talking about low power detection of underwater acoustic signals. So first I'll introduce myself briefly, and I'll talk about the basic ideas of minimizing the power used by detection of acoustic signals, and I'll give an overview of the solutions developed part of the project. And lastly, I'll give our plan for our contribution to the Unmanned project, which is also my PhD research. So, I earned my master's degree in electrical engineering and information technology from ENCORE this summer. I'm currently, for my graduate project, I work on the calibration of commercial and magnetic sensor nodes. You can see the calibrator and program is to control it. I'm currently a PhD student at the Laboratory for Intelligent Sensor Systems, where I'm working on low power embedded systems, embedded AI, and the detection of underwater events. So, distributed sensor nodes, continuous monitoring uses a significant amount of energy. For the acoustic signals which are of interest in underwater surveillance, those signals usually have a high bandwidth, which means they require high sample frequencies. And also the processing of algorithms used to extract the features from those signals will be quite complex. And the events being monitored are often short and sparse, which means that when using the classical approach of periodic sampling and processing, we waste a lot of energy when no events are present. So the idea to minimize the energy use is to use a wake-up sensing which can improve the sensor node autonomy significantly. You can see at the graph below that even though the wake-up sensing circuitry can increase the power used while on standby, the average power is still decreased significantly for short and sparse events being monitored. So, Awake was a project with the goal of improving the autonomy of subsea robotic sensor networks. Had the aim of developing an ultra-low power sensor interface for continuous monitoring and event detection, which could be used to wake up more power-hungry systems, and also a wake-up receiver for underwater communication systems. It lasted from 2017 until 2020. It was financed by the U.S. Office of Naval Research Global. It was a collaboration between this and the Sonar Research Institute. So the system developed as part of the Awake project consists mainly of two subsystems. First is the feature extraction subsystem, and second is the sequence recognition subsystem. The feature extraction subsystem contains three channels. Each of the channels contain a bandpass filter, channel detector, and envelope trackers and comparators. This essentially one bit digitizes each of the channel signals, which correspond to the signal in the frequency band defined by the input
filters and the thresholds for the comparators are programmable. So it can be used for different events. It can be extended with more channels depending on the so the pattern detection subsystem is essentially a template matching state machine. So it compares the output of the previous subsystem to a preset template which matches the event which we are monitoring. The states are defined by obviously the states of each of the channel and the duration of each state. This allows us to sample the signal only at the midpoints of state durations, which saves a lot of energy. The state machine is implemented in a low-power microcontroller. It stores 3 to 10 states, each lasting from 100 milliseconds to 10 seconds. And here we can see this graph shows the extension of lifetime of a sensor node with regards to continuous processing. So we can see that the shorter the event duration and the longer the inter-event period, the more energy we can save by using this wake-up system. So we can see that for one of the DSPs, the lifetime extension is almost 8 times. For the other, it's 2.5 times approximately. So for InnovaMare project, the aim is to develop an ultra-low power wake-up interface capable of diver detection. It is essentially a continuation on the system developed as part of the Awake project. But the area of research is ultrasound signals to see how they can be used. Detection, adaptive analog frontends, which would make the system more general and useful for more different events. Using AI on low power embedded systems and characterizing the trade-off between processing power, complexity of the algorithms, and battery life. Thanks everyone for your attention.
I have a question. How dependencies on the application exist in the how you're trying to get drivers because you can see them? Is it like you need to change a lot of things, or is it very dependent on the application when you implement the dependency?
Yeah, well, for the device developed as part of the Awake project, everything is programmable via I2C when system wake up, so you can easily program the system with a different pattern, different thresholds for the comparators, and also different center frequencies for the bandpass filters. So as long as the event can be detected by the 3 to 10 states, it can be characterized by 3 to 10 states. It can be the system can easily be adapted to detect it.
So you know something about the signal perception, right?
Yes.
The generic detector.
No. Yeah, you have to know the signal, and you have to think of a pattern which matches the signal, which is characteristic for the event you are trying to detect.
Maybe I don't know if you went about the book. I saw some people having the similar things on the beach. Be able to get ship noise from 2 or 3 kilometers.
Yeah, some tests were done with this system on detecting passing ships, but
system was underwater. I'm not sure how far away. So that's one of them. I think maybe even this is a spectrograph of a ship passing, for example.
Other questions? No? So I think then we can join and we'll have a bit more time. We're going to be just a bit program. Just a very so thank you again and see you again.
This Professor Maria, I forgot his name, that since in the beach, and even with waves, it was not like maybe 10 meters into the beach, like into the sea, basically. Passing, and like based on fish principles, and it was possible that ships passing